In nuclear engineering, prompt criticality is said to be reached during a nuclear fission event if one or more of the immediate or prompt neutrons released by an atom in the event causes an additional fission event resulting in a rapid, exponential increase in the number of fission events. Prompt criticality is a special case of supercriticality. Criticality. An assembly is critical if each fission event causes, on average, exactly one additional such event in a continual chain. Such a chain is a self-sustaining fission chain reaction. When a uranium-235 atom undergoes nuclear fission, it typically releases between 1 and 7 neutrons. In this situation, an assembly is critical if every released neutron has a 1/2.4 equals 0.42 equals 42% probability of causing another fission event as opposed to either being absorbed by a non-fission capture event or escaping from the fissile core. The average number of neutrons that cause new fission events is called the effective neutron multiplication factor, usually denoted by the symbols K-effective, Kf for K. When K-effective is equal to 1, the assembly is called critical. If K-effective is less than 1, the assembly is said to be subcritical, and if K-effective is greater than 1, the assembly is called supercritical. Nuclear reactors. In order to start up a controllable fission reaction, the assembly must be delayed critical. In other words, K must be greater than 1 without crossing the prompt critical threshold. In nuclear reactors, this is possible due to delayed neutrons. Because it takes some time before these neutrons are emitted following a fission event, it is possible to control the nuclear reaction using control rods. A steady-state reactor is operated so that it is critical due to the delayed neutrons, but would not be so without their contribution. During a gradual and deliberate increase in reactor power level, the reactor is delayed supercritical. The exponential increase of reactor activity is slow enough to make it possible to control the criticality factor, K, by inserting or withdrawing rods of neutron-absorbing material. Using careful control rod movements, it is thus possible to achieve a supercritical reactor core without reaching an unsafe prompt critical state. Once a reactor plant is operating at its target design power level, it can be operated to maintain its critical condition for long periods of time. Prompt critical accidents. Nuclear reactors can be susceptible to prompt criticality accidents if a large increase in K-effective occurs, e.g., following failure of the control and safety systems. The rapid, uncontrollable increase in reactor power in prompt critical conditions is likely to irreparably damage the reactor and, in extreme cases, may breach the containment of the reactor. Nuclear reactors' safety systems are designed to prevent prompt criticality and, for defense in depth, reactor structures also provide multiple layers of containment as a precaution against any accidental releases of radioactive fission products. With the exception of research and experimental reactors, only a small number of reactor accidents are thought to have achieved prompt criticality. For example, Chernobyl No. 4, the U.S. Army's SL-1, and Soviet submarine K-431. In all these examples, the uncontrolled surge in power was sufficient to cause an explosion that destroyed each reactor, and released radioactive fission products into the atmosphere. At Chernobyl in 1986, an unusual and unsafe test was performed that resulted in an overheated reactor core. This led to the rupturing of the fuel elements and water pipes, vaporization of water, a steam explosion, and a graphite fire. Estimated power levels prior to the incident suggest that it operated in excess of 30 gigawatts, 10 times times its 3 gigawatts maximum thermal output. The reactor chamber's 2,000-ton lid was lifted by the steam explosion. Since the reactor was not designed with a containment building capable of containing this catastrophic explosion, the accident released large amounts of radioactive material into the environment. The catastrophic fire in the graphite neutron moderator compounded the problem, sending massive amounts of radioactive debris into the atmosphere. In the other two incidents, the reactor plants failed due to errors during a maintenance shutdown that was caused by the rapid and uncontrolled removal of at least one control rod. The SL-1 was a prototype reactor intended for use by the U.S. Army in remote polar locations. At the SL-1 plant in 1961, the reactor was brought from shutdown to prompt critical state by manually extracting the central control rod too far. As the water in the core quickly converted to steam and expanded, the 26,000-pound reactor vessel jumped 9 feet 1 inch, leaving impressions in the ceiling above. All 3 men performing the maintenance procedure died from injuries. 1,100 curies of fission products were released as parts of the core were expelled. It took 2 years to investigate the accident and clean up the site. The excess prompt reactivity of the SL-1 core was calculated in a 1962 report. The delayed neutron fraction of the SL-1 is 0.70%. Conclusive evidence revealed that the SL-1 excursion was caused by the partial withdrawal of the central control rod. The reactivity associated with the 20-inch withdrawal of this one rod has been estimated to be 2.4% delta K, which was sufficient to induce prompt criticality and place the reactor on a 4-millisecond period. In the K431 reactor accident, 10 were killed during a refueling operation. The K431 explosion destroyed the adjacent machinery rooms and ruptured the submarine's hull. In these 2 catastrophes, the reactor plants went from complete shutdown to extremely high power levels in a fraction of a second, damaging the reactor plants beyond repair. List of accidental prompt critical excursions. A number of research reactors and tests have purposely examined the operation of a prompt critical reactor plant. CRAC, KWB, SPIRT-I, Godiva device, and borax experiments contributed to this research. However, many accidents have also occurred, primarily during research and processing of nuclear fuel. SL-1 is the notable exception. The following list of prompt critical power excursions is adapted from a report submitted in 2000 by a team of American and Russian nuclear scientists who studied criticality accidents, published by the Los Alamos Scientific Laboratory. The location of many of the excursions. A typical power excursion is about 1 by 1,017 fissions. Los Alamos Scientific Laboratory, the 11th of February 1945. Los Alamos Scientific Laboratory, December 1949, 3 or 4 by 1,016 fissions. Los Alamos Scientific Laboratory, the 1st of February 1951. Los Alamos Scientific Laboratory, the 18th of April 1952. Argonne National Laboratory, the 2nd of June 1952. Oak Ridge National Laboratory, the 26th of May 1954. Oak Ridge National Laboratory, the 1st of February 1956. Los Alamos Scientific Laboratory, the 3rd of July 1956. Los Alamos Scientific Laboratory, the 12th of February 1957. Mayuk Production Association, the 2nd of January 1958. Oak Ridge Y-12 Plant, the 16th of June 1958. Los Alamos Scientific Laboratory, Cecil Kelly Criticality Accident, the 30th of December 1958. SL1, the 3rd of January 1961, 4 by 1018 fissions are 130 megajoules. Idaho Chemical Processing Plant, the 25th of January 1961. Los Alamos Scientific Laboratory, the 11th of December 1962. Saroff, the 11th of March 1963. White Sands Missile Range, the 28th of May 1965. Oak Ridge National Laboratory, the 30th of January 1968. CHELYABINSK-70, the 5th of April 1968. Aberdeen Proving Ground, the 6th of September 1968. Mayuk Production Association, the 10th of December 1968. Kurchatov Institute, the 15th of February 1971. Idaho Chemical Processing Plant, the 17th of October 1978. Soviet submarine K-431, the 10th of August 1985. Chernobyl disaster, the 26th of April 1986. Saroff, the 17th of June 1997. JCO Fuel Fabrication Plant, the 30th of September 1999. Nuclear weapons. In the design of nuclear weapons, on the other hand, achieving prompt criticality is essential. Indeed, one of the design problems to overcome in constructing a bomb is to contract the fissile materials and achieve prompt criticality before the chain reaction has a chance to force the core to expand. A good bomb design must therefore win the race to a dense, prompt critical core before a less powerful chain reaction disassembles the core without allowing a significant amount of fuel to fission. This generally means that nuclear bombs need special attention paid to the way the core is assembled, such as the novel implosion method hypothesized by Richard C. Tolman, Robert Serber, and other scientists at the University of California, Berkeley in 1942.